Topic for today's video is going to be section R8, roots and radicals. This is there's sort of kind of three purposes on why we're covering this section. For the square root part of what we're doing, the main reason we're covering that is here in a couple sections we'll be talking about quadratic equations and quadratic formulas. So we need to know how to simplify our square roots. Some of this stuff, especially dealing with like rewriting radicals as exponents. When we get to unit 4 and deal with logarithms, that's going to pop back up. And then the rest of what we're doing with the radicals, that's really sort of the pre-calculus sort of level of stuff. We don't use a lot of that, like the adding and subtracting or the foiling. We don't use that much in this class. But it's relatively straightforward content, so this is a good place to cover it. So as always, I am working from the resources, the lecture outlines that I put in Blackboard. And so there are 3 pages worth of notes or examples on this. So if you've been watching my videos, just go to the student resources for Unit 1 folder, lecture note outlines. And as always, if you're on campus, come by and see me, and I've got printouts of all this for my in-person classes. I might save you some printing if you're on campus. All right, so let's get into the video. Real quick, just to look at our objectives for today. So simplifying radicals, that's what we're going to spend most of our time on. Foiling radical expressions, again, I use FOIL and multiply interchangeably. I've noticed now those are the main things. I do notice that now I've left off add and subtract. Spell today. Of course, we're going to add subtract these radical expressions. That's again, those last two are a little bit more of the pre-calculus sort of stuff. And then what else? Oh, and rationalize denominators. That is specific, that is pre-calc. If you're going on to trig, that's something that you're going to see a fair amount. But again, we're going to kind of cover the basics of it. We're not going to do the messy stuff, since the vast majority of you aren't going to need it for anything more than the basic ones we cover. All right, so that is what we're talking about today. And this will be the last video for like the intermediate algebra, or like lower level intermediate algebra, algebra 2 sort of stuff. And then our next videos we'll start getting into solving equations, quadratic stuff, so it'll be a little bit higher stuff. But this is, to me, this is like the first half of the view material. Theoretically, anything that's in those R chapters you're supposed to already know. But the reason we're covering it is we need to make sure you know it if you haven't seen it in a while or at all. So, all right, let's get into the content. Oh, by the way, if you don't have one with you, grab your calculator and not your phone calculator, because those you can't use your phones on the test. And so whatever calculator you're going to be using for the test, this is definitely one of those sections where a calculator comes in handy. So part of what I'm going to do today is, at least with my basic scientific calculator, make sure that you can do these on the calculator as well. All right, so let's start with really basic question. What is the square root of 81? So when it says simplify that, what does it mean? Well, it goes back to the definition of what is a square root. Well, the square root is what number times itself, gives a number on the inside. So most of the double digit numbers I expect you to know. If you're starting getting into triple digit numbers, then calculators come in more handy. But 9 times 9 is 81. So square root of 81 is 9. Square root of 64, well, 8 times 8, 64. And one thing, especially if I've done this in a while, is when once you simplify it and get the number that you're multiplying by itself, drop the square root. Sometimes I'll see students that'll say like the answer is square root of 8, not 8 itself. So once you identify the number being squared, just the number itself is the square root. If you haven't seen square roots in a while, a common mistake is people tend to divide by 2. So like sometimes for square root of 64, I see students do 32. But remember, that square root it looks a lot like the division symbol, but it's got that little check on the front. So just watch out for that. All right, what about number 3, negative square root of 16? Can we deal with negatives and square roots? Well, when it comes to order of operations, that negative outside, this is the opposite of the square root of 16. So we're doing the square root of 16 first, bringing that negative over. And what is the square root of 16? That is 4. So the answer would be -4. So we're fine if we have negatives outside our square roots. It just means the answer is going to be negative. What about the square root of -36? What number times itself gives us -36? So this is where we're starting to run into problems, right? Because if you do 6 times 6, that's a positive 36. If you do -6 times -6, once again, that's a positive 36. If you're thinking -6 times +6, yes, that does give us -36, but the numbers have to be the same. So one being positive, one being negative, that's not going to work. Well, when in doubt, go to the calculator. Try to get there without a glare where you can see the whole screen. So square root, and all calculators are different. For the ones that I like to use, anytime you have your symbols above your buttons, that's when you're going to use your second or your shift, depending on the calculator. So I just do second, and then x squared gives me square root. So I do negative. Oh, when you're doing negative, make sure that you're using your calculator's negative button, not the subtract button. There is a difference. So square root of -36, hit enter, you get domain error. All right, so what does domain error mean? Well, we'll talk more about domain and range in later chapters or later units, but domain is like the X's you can plug in to get an answer. So when you're getting a domain error, that means that there are no answers, well, no real number answers. So the actual answer to this is no real number answer. So it's not that there's no answer, there's no real number answer. And so let's see, our next unit is 1.1, solving equations. So after that, we're going to do 1.3, which is complex numbers or imaginary numbers. There is an imaginary result to that. So if any of you remember the I, the imaginary answer to this would be 6i. But when we're in this section, our answer is going to be no real number. Once we cover complex numbers in 1.3, then there is going to be an answer with the imaginary number, but that's why it's no real number answer. So just be aware of that. You cannot take square roots of negative numbers. Negative on the outside is fine because you're just doing the opposite of whatever your positive answer is. Not allowed to do square roots of negatives, which again, why your calculator is giving you an error message. Now, we don't do this often. This might be something more like you see in a science class, but square root of 0.25. Okay. Nice thing about this is it's a clear English calculator for things like this. So that's what 0.5. Okay. All right. Now, all of these, well, other than the number 4, are what we call perfect squares. Right? Because 9 times 9 is 81, 8 times 8 is 64. We're going to do a lot of numbers, particularly with our quadratics, that we're dealing with numbers that are not perfect squares. So, for example, if you want to take the square root of 70, well, 70 is not one of these perfect numbers. 70 is between 64 and 81, so the answer should be between 8 and 9. So we're going to have to know how to deal with that as well. We'll do that a little bit later in this video, but just these are the perfect square numbers, like 100, square root of 100 is 10, square root of 121 is 11, 49, square root of that is 7. So we like those square root numbers, but very often we're going to deal with messier numbers. Now, before we get that, let's look at some cube roots. For this class, we don't use cube roots near as often. Those are saved a little bit more for higher level classes. So what about the cube root of negative 512? Actually, let's do the cube root of 64 first, and we'll come back to that. So what does a cube root of 64 mean? Well, a cube root means what times itself 3 times. So if you look at that and you're thinking 8, you're thinking square root. A square root doesn't, this is what we call the index. So there's the cube root. If we put a 4 on it, it's the 4th root, and so on. That's for square roots. If there isn't a index, it's assumed to be 2 a square root. But a cube root, it now means what times itself 3 times gives us that number. Okay, so if you're thinking 64, the cube root of that is 8, you're thinking square root is 8 times 8 is 64. So how do you find the cube root of a number? Well, before we jump to the calculator, just do the cube root directly on that. Well, what you could do is, what is 1 cubed? What is 2 cubed? What is 3 cubed? What is 4 cubed? And so on. Excuse me. It turns out that, let's see, 2 cubed is 8, 3 cubed is 27, 4 cubed is 16 times 4, that is 64. So what's the cube root of 64? It is 4. It's 4 times itself gives you 64. All right, so now back to 6, that cube root of negative 512. When you see that, is it like number 4 up here where there's no real answer? Because there's a negative on the inside. Well, the answer is there is a real number answer, because for cube roots, we can do if we do a negative times a negative times a negative 3 times, you're going to get a negative answer. And so it turns out that any even root can't have a square root on the inside, a negative on the inside to get a real answer. So square roots, 4th roots, 6th roots, 8 roots, we don't want the negative on the inside. If it's odd roots, 3rd root, 5th root, 7th root, and so on, we can have negative radicands is what they're officially called, because when you multiply an odd number of negatives, you are getting a negative answer. But what that tells us is the answer is going to be negative. And so now, how do we get the cube root of 512? Well, you could do it the same way here. Obviously, we keep going until we get to 512. Or how do you do it on your calculator? So again, all calculators are a bit different. This calculator might be a little hard to see because of Zoom. I'm sorry. That is X up in the index and then the square root. So that's a caret or the hat, that's the exponent key. So for this calculator, if I want cube root, I have to do 3 first, and then do second, and then that button. And so notice now that it's not the square root symbol because that 3 is up there in the index. So I put in negative 512. The answer is negative 8. Because 8 times 8 times 8 is 512, and then we need the negative to get the negative answer. So as you're going through the homework, play around with the calculator, make sure you can do square roots, cube roots. 4th root, 5th root would be the same way. You just do the 4 or the 5 first. Some calculators are a little bit different. So whatever your calculator is, make sure you can operate. Okay. Here's a quick question. Number 8. There's a negative inside there, so that means there's not a real number answer. Well, we have to do order of operations. And so order of operations, radicals are like grouping symbols, just like brackets or big parentheses or anything like that. And so when I see this, that exponent is inside the grouping symbol, so we got to do negative 9 squared first. So negative 9 times negative 9, we get positive 81, and then the square root of 81. We've already did it in 31. That's 9. So just because we have negatives inside a square root doesn't mean we can't deal with it. But in this case, that's because we're squaring it basically together. Just watch out for that. Like I said, in order of operations, radicals are grouping symbols. All right, real quick here, fourth root of 16. Well, what does that mean? That means what number times itself 4 times gives us 16. A hint, these numbers grow really fast. So if you do 2 to the fourth, 2 times 2 is 4, times 2 is 8, times 2 is 16. And if you do 3 to the fourth, 3 times 3 is 9, times 3 is 27, times 4, 3, that does give us the 81. So these numbers, when you start raising your power, grow pretty quick. So the fourth root of 16 is 2. The fourth root of 81 is 3. And again, you can do these on your calculator. So if I want the fourth root of 81, I would do 4, and then second square root sign, or radical sign, and then 81. Bam, there you go. Okay. All right. So this is the warm up. Those are simplifying the perfect squares. And so let's talk about simplifying when they're not perfect squares and when we're simplifying variables. So something that comes up, and we're going to see this again when we get into logarithms, unit 4. This is a fairly important definition. But we can actually rewrite radicals as fractional exponents. And I'm going to put some numbers to this so you can see a little bit better. But if you have the x to the a power, the nth root of that, the way that you can write that as an exponent is, one, we're going to have a fractional exponent. The inside exponent is going to be the numerator. The index of the radical is going to be the denominator of that exponent fraction. So, for example, you have x to the 1/2 power. And if we're going to rewrite that, well, what root would that be? Well, the denominator is 2, so that means we're going to have the index of 2, and then on the inside would be x to the first. Of course, the way we would write that for final answer, if the index is 2, it's we don't need to write it, it's understood to be 2. We don't need that exponent of 1, that's understood. So the square root of x is the same as x to the 1/2. We had, let's see, cube root of x. How would we write that as a fractional exponent? The index is the denominator of the fraction. The exponent on the inside, which in this case is 1, will be x to the 1/3. So if we had the fourth root of x, it'd be x to the 1/4 power. If we had the fifth root of x, it'd be x to the 1/5 power, and so on. Okay. So as we're going through these problems, simplifying these radicals with variables and numbers, keep that in mind. And like I said, we're going to definitely see this again in text 4. All right, so one of the ways that we can use this to simplify, well, let me back up. So now when we're going to be simplifying radicals, there's two sort of ways that we can simplify radicals by hand. One is the grouping method, and then one is going to be using this idea here. I call that the division method, and so let me show you both. Okay, so this first example, the cube root of y to the 7th. So let's look at what the grouping method would look like. Okay. So when we're simplifying radicals, basically what we're trying to do, like when we simplify the square root of 81, the reason it's 9 is basically we're trying to pull out the perfect squares and perfect cubes outside the radical and then see if there's anything left over. So for these perfect squares, it was like nothing left inside the radical because 9 times 9 was 81. So what we're looking for in the grouping method is we want to find perfect squares, perfect cubes, perfect fours, whatever the radical is. And then for every one of those, we're going to pull one out. Let me back up with that 81. So if we did that by grouping method, we know that 81 is 9 times 9. So since it's a square root, we're looking for pairs. So I have a pair of 9s. And so since I have one pair of 9s, one is going to get pulled outside the radical. And then there's nothing left. That's why the answer is just 9. So let's do the cube root of y to the 7th the same way. All right, so first of all, y to the 7th is 7 y's. So write that out. 2, 3, 4, 5, 6, 7. All right. Since we're doing cube root, we're not looking for pairs like square roots. We're looking for triplets. So we want 3 of a kind. So there is 3 y's. There's 3 y's. And we have 1 left over. So how does that give us our answer? Well, I have 2 y's that I'm pulling out. So that gives me y times y, or y squared. And then inside, we have a y left. It is cube root, so don't forget the 3. So the cube root of y to the 7th simplifies to y squared times the cube root of y. Because we have, the cube root says we have those two groups, and then we have 1 left over. Let me see. Yeah, so that's a grouping method, and then let me show you the division method, and then as we do the examples, we'll do both. Most people, I think, when you first see this, I think the grouping method is a good place to start, and then as you get more practice, you can maybe do some of the division method sort of as a short. Now, for the division method, this relies on what we were talking about earlier on how you can rewrite radicals as fractional exponents. So what we do first here is we rewrite this as a fractional exponent. So it's going to be y to what power? Remember, the index just goes on bottom. The exponent on the inside goes on top. So the cube root of y to the 7th is equivalent of y to the 7/3 power. So how does that help us simplify this? Well, the reason we call this division method is we're going to take that the 7/3, and we're going to divide this. We're going to do long division. We're not going to do decimal division. We're going to do long division with a remainder. So we always do the top divided by the bottom. We're doing 7 divided by 3. And so 3 will go into 7 twice. And when we subtract that, we get a little remainder of 1. Okay. And so how does that give us our answer? If we're simplifying the cube root of y to the 7th, so what this whole number part, that is our outside exponent. So since we have 2 for that long division, that would be y squared. And then the remainder is the inside exponent. Spell exponent. So inside we have a y to the 1st or just a y. Notice we get the same answer, y squared times the cube root of y squared times the cube root of y. So once you get a little bit more comfortable with this, notice that the reason we're getting a 2 is there are 2 groups of 3 up here. And the reason, and then the reason we're getting a remainder of 1 is there was 1 left over. So you see why I say, like, sometimes it's easier to start the grouping method, and then as you get more comfortable with it, go to this. To me, this is like a quicker way. Like if you had, say, y to the 50th, you would not want to write out 50 y's. That's where the division method comes in handy. Okay. So these are the two methods we're going to use to simplify radicals. Let's put this to a little bit bigger examples. All right, number 13 is the square root of 9y to the 8th. My first recommendation on this, anytime you're simplifying a radical that has numbers and variables, you can split this up and do just the numbers with the numbers, and then just if you have more than one variable, like the x's with the x's, y's with the y's, and so on. So we're going to break this up into the square root of 9 and the square root of y to the 8th. Well, hopefully the square root of 9, you're comfortable with that being 3. The grouping method is a good way to show that because 9 is 3 times 3. We're dealing with square roots, we want pairs. So that's just 3. What about the square root of y to the 8th? We're doing the grouping method. We need 8 y's, 4, 6, 7, 8. Now we're doing square root. So for square root, you want groups. The group is a pair. So there's a pair of 8s, pair of 8s, pair of 8s, pair of 8s. So what is outside the radical? Well, how many pairs of y's do we have? 1, 2, 3, 4. So there's y to the 4th on the outside. What's left inside the radical? Well, nothing, because we had no y's left over. So these are perfect squares. Right? And so once you simplify each one of them, now we know our answer is 3y to the 4th. If you want to use the division method here, well, we don't need it for the numbers. Grouping method and calculator are used for the numbers. This division method really comes in helpful with the exponents. So we're going to use division method. We're going to do 8 divided by 2 because we're doing square roots. Well, that is 4 with no remainder. And so if you notice, 4 is y to the 4th because that's the whole number answer is what's outside. There is no remainder, so there is nothing inside the radical. Yep. The main thing you have to be careful of with the grouping method is, are you doing square roots or cube roots or fourth roots, whatever? So if it's square root, you're looking for pairs. If it's a cube root, you're looking for triplets. If it's a fourth root, you're looking for them in groups of 4, and so on. Yeah. How about, let's show you here. Number 14, the third root of negative 8 x to the 12th, y to the 12th. I don't know if it's my eyesight or if it's just the camera that looks a little out of focus. I apologize. Okay. Let's write this a little bit bigger. We have the cube root of negative 8 x to the 12th, y to the 12th. Actually, let's modify this a little bit. Let's make this y to the 10th. That way we'll get more out of this example. So I'm going to call this 14. So let's do the numbers with numbers. So let's do the cube root of negative 8, and the cube root of x to the 12th, and the cube root of y to the 10th. So what is the cube root of negative 8? What times itself 3 times gives us negative 8? Well, for these smaller numbers, hopefully you'll see enough of these. Hopefully you can get a little bit up to speed doing it without a calculator. But again, if you need to, don't worry. Use your calculator on the numbers as a backup. That's fine. Now, what about the cube root of x to the 12th? Well, if you want to do it by grouping method, you have to write out a few x's here. 12 to be exact. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. So the grouping method, this is a cube root, so we'll have triplets, groups of 3. So 1, 2, 3, 4. So how does that simplify? Well, we have 4 groups, so that would be x to the 4th on the outside. What's left on the inside? Nothing, because there is nothing left over. Or want to do the division method, what is 12 divided by 3? It is 4 with no remainder. So there's our x to the fourth with nothing left on the inside. All right, so what about the cube root of y to the 10th? Again, I want to do this both methods just to show you 4, 5, 6, 7, 8, 10. So just like with x, this is cube root, so we're looking for groups of 3. So how does that simplify? We have 3 groups of y, so it'll be y cubed. What's left over is a single y. This is a cube root, so don't forget your cube root. All right, so how do we do that with the division method? Well, if you do 10 divided by 3, it'll go in 3 times with a remainder 1. So that 3 is our y cubed. That remainder of 1 is y to the first on the inside. So what is our answer? Number-wise, we have -2. Variable-wise, we have an x to the fourth and a y cubed on the outside of the radical. And then inside the radical, we have cube root with 1. All right, I'm going to pause this right quick, see if I can make this a little bit clearer. All right, that looks like sorry, I didn't do that sooner. That looks like, I don't know about you, that looks much easier to read to me. All right. So this is how you're going to simplify radicals in general. Okay. Now, both the numbers we did this time had nothing left over, but if it's not a perfect square or perfect cube, we can do the grouping method on that. Let me see. Let's see what the next examples are. Show you. Yeah, let's jump to number 16. And so we can simplify one of these. It's not a perfect square on the number part. So 16 is the square root of 320, x to the 7th, y to the 8th. So we're going to split this up into 3 parts. Square root of 320, square root of x to the 7th, square root of y to the 8th. All right, now when it gets to your bigger numbers, your triple digit numbers, I don't expect you to know these like I expect you to know your perfect square 2-digit numbers. So let's see what the calculator gives us with the square root of 320. It's giving me 8 square root of 5. Now that's what my calculator is giving me. For some of you, if you're getting that decimal 17.888, this is one reason I like scientific calculators is they are set up, or they're either set up to give you this is what we call the exact answer. This is a decimal approximation. If you have a graphing calculator, to be honest, I don't know how to get this answer in a graphing calculator. You might have to Google that. I think graphing calculators by default give you always just a decimal approximation. Now, if you have one of these calculators and you're getting a decimal approximation, that I can show you how to fix. Because on these calculators, you see that the mode button, and down at the bottom, there's the classic and the math print. The math print is like the fraction friendly and the square root friendly version. If I go down there and hit classic, and it's highlighted now, hit enter. And so what happens when I go back, say that I do like square root of 50, it's going to give me a decimal number by default. It's if you want the radicals by default, for these calculators, you have to make sure that they're in math print. And then your second quit will get you back to the goal. Now, how did I get that decimal to pop up? So let me go back to the square root of 320. So now I'm back in math prep mode. And so how do I get a decimal out of that? Well, every calculator is different. For these calculators, you see that double arrow key right above the enter sign. If I hit that, it takes me back to decimal form. Hit it again, it takes me back to square root form. A lot of calculators have an S to D button right there. So I don't know, standard to decimal maybe. But that's one thing, like I said, whatever test you're going to be using or calculator you're going to be using for the test, make sure you're doing it in your homework and your practice and things like this. Now, where did that come from? Okay. So if you don't have a calculator that can do this and you need to reproduce it, well, think about the grouping method. Well, to do that, you're going to do a factor tree. So give me something that will divide into 320. Yes, it is even, so you can start with 2, but if you start with 2 on a big number like this, you can have a lot of branches. I like to start with 10 because that has a 0 in it. And then 10 is 2 times 5, 32, 4 times 8. And then 4 is 2 times 2, 8 is 2 times 2 times 2. All right, so what do we have? We have 1, 2, 3, 4, 5, 6 2s. And a 5. So how does that help us? Well, remember the grouping method says that this is square root, so we're looking for pairs. So there is 1 pair of 2s, 2 pair of 2s, 3 pair of 2s. So what are we pulling out? That is 2 cubed. What's left over is a 5. Now what is 2 cubed? Bam, it's 8. So that's where that 8 square root of 5 is coming from. So if you don't have a calculator that will give you what we call the exact answer or the answer in a radical form, if you're trying to simplify numbers like this, you're pretty much going to have to do your factor trees to get the complete prime numbers and then do your grouping method. Or, like I said, this is one place where I'm more than acceptable of being able to use your calculator for this part. Okay, then we got x to the 7th and the square root of x 7th and y to the 8th. You can do grouping method if you want. I'd like to, at this point, I'm doing the division method. 7 divided by 2 is 3. Remainder 1. That's going to be x cubed times square root of x. We got 3 on the outside, 1 on the inside. For y to the 8th, 8 divided by 2 is 4 with no remainder. I'm going to have y to the 4th on the outside, and then no y's on the inside. Like I said, or again, you can do your grouping method and look for pairs because we're dealing with square roots. Right, this is getting kind of messy, so we'll put the answer here. All right, so for answer-wise, what do we have outside the square root? Well, we have an 8, x cubed, over y to the 4th. What do we have inside the square root? We have a 5, and we have an x. Okay. So when it comes to simplifying radicals that are not perfect squares, like 81 or 25 or 36, you got to do a little bit of work. Either the grouping method, or especially for variables, the division method, whichever works for you. I recommend that you practice both in the homework because it's always better, I think, if you have more options on how to do these problems. And sometimes, one option really works better for you, and maybe another option works better for somebody else. Like for me, I think starting here is nice, but especially if it gets messy, like big exponents, I definitely want to do the division method. Right. That is simplifying basic radicals. All right. Yeah, let's talk about some adding and subtracting. This is something that we don't do a lot for this class. Again, this is kind of dipping our toe into some of the waters that you need for pre-calc. It turns out that adding subtracting radicals really isn't that bad if they're like radicals. And what do I mean by like radicals? That means they have the same root or same index with the same radicand, which is what's on the inside. It's sort of like adding fractions with the same denominator. Okay. So if you have 2 cubed root of 3 plus 8 cubed root of 3, how do you add those? Think of it as a fraction, or think of it as like an x. So if you had 2x plus 8x, what is that? That's 10x. Well, 2 cubed root of 3 plus 8 cubed root of 3 is 10 cubed root of 3. So when you're adding subtracting like radicals, you're adding subtracting the coefficients, keeping the radical the same. Now, if they're unlike radicals, well, let's do 19 right quick. So we have square root of 3 minus 12 square root of 3 plus 4 square root of 3. What are you getting as an answer for that? Now, the straightforward part is they're all square roots of 3. So that's going to stay the same. So how many square roots of 3 do we have? If you're thinking -8, you fell into my trap. One thing you have to be careful of, that is a 1 square root of 3. So you may want to put that 1 there because it's easy to overlook. So now we're doing 1 minus 12 plus 4, which actually gives us -7 instead of -8. So that would be -7 square root of 3. So if you have like radicals, that's very straightforward. To me, that's just like adding like x's with x's or adding fractions that have the same denominator. And you can't add like square roots. You can't add like if we have like a square root of 2 and a square root of 3, with the radical being the radicand on the inside being different. That's like trying to add unlike denominators. Now, unlike denominators is a much easier fix on how to get them the same than it is with unlike radicals. So for the most part, if they can't simplify to the same radical on the inside, we're not going to mess with it. That's a higher level thing. The other thing to watch out for is we can't add square roots and cube roots. So if that was like square root of 3 and cube root of 3, we're definitely done because we cannot add those. Again, not without higher level mathematics of getting them the same, and we're not going to deal with that. But we are going to deal with some problems that may look like they're unlike, but really aren't. So what we're going to do is if you get a problem like number 20, where's my scrap? Okay, so number 20 is 5 square root of 2 plus 6 square root of 18. Okay, so when you're looking at that, we're trying to add them. Hopefully the first thing that kind of pops in your brain is those are unlike radicals because they have different numbers on the inside, so we can't add them. Okay, that's a good first step. But the question is, can we simplify this? Because if we can simplify this and make this a square root of 2, then we can actually do the addition. So I'm going to do this two ways. I'm going to do it by hand, and then I'm going to do it by the calculator. So that way you have both tools in your toolbox. And then I'll talk about like proper ways to use the calculator on this. So how do we simplify 6 times square root of 18? I'm going to leave 5 square root of 2. That's a 2. We can't simplify that. It doesn't break down. But what can we do with 18? Think of this as factor tree. 18 is what, 6 times 3 or 9 times 2. 6 is 2 times 3. If you did 9 times 2, you'd still get 2 3s and a 2. So how does that simplify? Well, first of all, that is 6 times square root of 18, so you may want to put that multiplication dot there. But how do we simplify that square root of 18? Well, we have the square roots, we're looking for pairs. We have a pair of 3s. You pull that 3 out. So it becomes 6 times 3, and then we have square root of 2 left over. And how do we deal with this? Well, 6 times 3, that's outside the radicals, that would be 18. which that's just coincidence that the 18 and up on the outside, those are just way than, if that hadn't been a 6, it would have been an 18 out here. But by simplifying that, we now have square root of 2, square root of 2, so this can actually be added. So 5 plus 18 is 23. We have 23 square root of 2. All right, so that's doing it without a calculator. All right. Which the close equivalent of what we're dealing with is dealing with fractions that have different denominators. This is sort of kind of like that. Let's see how we use the calculator here. So question, can we do this in the calculator as is? Well, let's try it. So 5 square root of 2. Now notice that the cursor is still inside the radical, so use your arrow key to get it out. Plus 6 square root of 18. Oh, now notice I did 6 squared. You don't have to erase the whole thing. The nice thing about the calculator is like this, you can arrow over. Let's see, I want to delete that. Delete. And then now let's go back and do square root. If the deleting part throws you off, you can always just start over. All right, so when I hit enter, it gives us 23 square root of 2. So theoretically, you could put problems like this in your calculator all at once. But what do you think as a math teacher I'm going to say about that? Yes, you could, but you can do that and have absolutely no knowledge whatsoever of what we're doing, which, let's be realistic, that's not what we're trying to do, right? So here's what I would like to see you do, how to use your calculator on this. So we're going to compromise. So here's my compromise, is use the calculator to simplify. And so how do you simplify 6 squared root of 18? So 6 squared root of 18 is 18 square root of 2. And so I then do this without a calculator. Because I want you to recognize the fact that those are both square roots of 2. So then we're just adding the coefficients. If you want to calculate for 5 plus 18, that's fine. But you get what I'm saying of like, don't use the calculator for the entire thing, because we're not trying to completely bypass, your knowledge part of this. There's no critical thinking going on if you just plug that whole thing into the calculator to begin with. There's still some critical thinking if you can deal with this without the calculator. How about 21? We have square root of 2 plus 4 square root of 72 minus 2 square root of 32. All right. And one of the things here is like, often these problems they're going to kind of give you a hint, like this we can't break down to. So if we can get all these simplified to square root of 2, then we can do some adding. There is no guarantee that these will simplify to square root of 2. So let's see what happens. Okay, so following the previous example, let's do this in the calculator. And let's go ahead and put a 1 in front of that square root of 2 so we don't miss it. And so what does 4 square root of 72 simplify to? That's 24 square root of 2. And then minus, what is 2 square root of 32? That is 8 square root of 2. So like I said, to me, that's a good use of the calculator. Now we have square root of 2, square root of 2, square root of 2. They're all like radicals. So now we can add, subtract them. So that's 25 minus 8 is 17 square root of 2. Quick question. What if this was, what if when we simplified it, we got down to 1 square root of 2 plus 24 square root of 2 minus, what if it come out to 8 square root of 3? What if that's what happened when we simplified it? What would we do then? And this is why I still want that critical thinking. That's why I don't want you to start at the beginning, because the calculator can give you an answer to this and you could not know why. But here, those are the like radicals. So those are the ones we can add. So that would be 25 square root of 2. That does not square root of 2, so we can't add or subtract it. So then we'd be done. This is sort of like having x plus 24x minus 8y. You can add the x's, but you can't add the y's with the x's. Right? So if they're unlike radicals, you cannot add or subtract them. Right, so that's we could theoretically put variables inside these radicals, and then we would get back to giving you problems that might look like this on the inside and have you add subtract them. We're not going to get that messy. I'll save that for those that are going on to calculus. All right. That's adding, subtracting. Let's talk about multiplying. All right, so multiplying radicals, again, multiply and divide pretty much always has different rules than add, subtract. And so when we're multiplying radicals, what you have to do, one, they have to be the same root. So you multiply cube roots with cube roots, square roots with square roots, and so on. Don't multiply cube roots with square roots. Again, theoretically, there is a way you can do that. That is far beyond the scope of what we need for this class, so we're not going to discuss it. All right. And then once once you identify you have the same radical, the same index, the way that you multiply your radicals is you multiply outside terms with outside terms, inside terms with inside terms, and then you may have to simplify the inside part. Okay, so do not multiply something outside a radical with something inside a radical. That's the big no-no. All right, so let's do some examples of that. So if 22, we have cube root of 14 times cube root of 3. So they're both cube roots. And so the way we do that is just 14 times 4. What was that, 52? No, sorry, 56. All right. Does that simplify? Now here's what you have to be careful of with calculators is they're real good with square roots, not so much cube roots. So remember to do cube roots on the calculator. On this calculator, at least I can do 3 first, and then that x root, that 56. Notice that gives me a decimal, and if I do the double arrow key, it gives me a decimal back. So these, even the scientific calculators that are radical friendly, that's for square roots only, not cube roots. So how would that simplify? Well, it comes down to, to the grouping method again. We could do factor trees for 56. The nice thing about it is let's factor the smaller numbers first. So 14 is 7 times 2, and then 4 is 2 times 2. And so if you notice, we're doing cube root, so we need a group of 3. There are 3 2's, so 1 2 comes out, and we're left with a 7 on the inside. In the homework, I don't even know if it gets this messy with simplifying after, but that is something that you have to watch out for. It's just like a fraction. Never give me a fraction that's not simplified if you want to get full credit. So when dealing with radicals, don't ever give me a radical as an answer without seeing if you can simplify it if you want full credit. It's not that this would be wrong. It's just math would count wrong. I think that is not finished. Okay. All right, let's look at 23. And I'm going to pull up MATLAB here at the end, and we're going to go through some of the examples to kind of see how messy they get. what do we have? We have 2 square root of 7x cubed times 5 square root of 7x to the 5th. Then you're multiplying radicals, you multiply outside with outside. So we're going to do 2 times 5. And then we're going to do inside with inside. So inside the square root, we're going to have 7x cubed times 7x to the 5th. Okay, so outside we have 10. Now here's a recommendation. Is yes, you could multiply that and get 49x to the 10th or x to the 8th. But aren't you going to have to try to simplify this? So let's do, instead of doing this, let's skip down and go straight to the grouping method. Notice we have 7 times 7, so let's put those together. So how many x's do we have? Well, 3 here, 5 here. So there is a pair of 7s. Then we have 1, 2, 3, 4 pairs of x's. So what's going to come outside the radical? Well, there's 1, 7. And then 1, 2, 3, 4 pairs of x's, so that would be x to the 4th. With nothing left over, because there's no 7s left, there's no x's left. So that would be 70 x to the 4th. You could also get from here, because what is the square root of 49? It is 7. And then if you're using the division method, you're doing 8 divided by the index of 2. 8 divided by 2 is 4 with no remainder. So when you're multiplying radicals, multiply outside with outside, inside with inside, and then simplify, see if you can simplify the inside. Sort of like when we were simplifying the rational expressions from R7, it's like a longer simplified problem. To me, it's sort of like a longer simplified problem as well. All right. How about, so that is like that's sort of like a monomial times a monomial, because there's no adding or subtracting going on. What would you do with number 24? The square root of 3, parentheses, square root of 5, plus square root of 7. Well, what kind of problems does that look like? Hopefully that looks like a distribution problem, which that is exactly what that is. Because inside, we can't add those because they're different numbers inside the radical. And those are both prime numbers, so they're not going to simplify. So how do we do this? Well, square root of 3 times square root of 5 is square root of 15. And plus square root of 3 times square root of 7 would be square root of 21. Now, does that simplify? Always check to see if it can simplify. Well, we know 15 is not going to simplify because if you think of it as grouping method, how did we get the 15? We had 1, 3, and 1, 5. There's no pairs in there, so that doesn't simplify. 21 was from a 3 and a 7. There was no pair there. So neither of these simplify, and so you're done. How do you know for sure? Go back to this. So if we do square root 15, arrow over plus square root of 21. Notice it gives me square root of 21 plus square root of 15. Change the order for whatever reason, but notice there are no new numbers. So that's when you put in square root of 21 and get square root of 21 back, it tells you that it's already simplified. There is nothing you can do to simplify. And again, yes, you could have put this whole problem in here at the beginning, but then you're completely bypassing what is a fairly basic concept that we use over and over again in this class of distribution. Okay. And if you do this sort of problem on the test, tricking a calculator and get a wrong answer, don't expect partial credit. All right, so like at least like show your arrows to show that you kind of know what the process is. Let's do one more of these. So square root of 5 times square root of 35 and square root of 5 times -4 square root of 5. Okay. Well, how do we multiply these? Well, 5 times 35. 175, so square root of 175. Now, how do we multiply square root of 5 times -4 square root of 5? Well, this is essentially a 1 square root of 5. Remember, we're multiplying outside with outside. We're doing 1 times -4, so it'd be -4. And then inside times inside, so square root of 5 times square root of 5, which is square root of 25. Are we done? Well, we don't know until we try to simplify. I'm hoping that you look at square root of 25 and recognize that's 5. So we have -4 times 5, so that's going to be -20. All right, does square root of 175 simplify? Once you get into those triple digit numbers, again, I'm okay with you kind of going to the calculator. The square root of 175 is 5 square root of 7. And then those are definitely, one has a radical, one doesn't. So we're done because we can't subtract those. Now, how does 175 become 5 square root of 7 if you don't have a calculator all at once? Well, you kind of need your factor trees. And it turns out that if you do your factor tree for 175, well, it divides by 5. Well, how do we get the 175? We did 5 times 35. And then 35 is 5 times 7. So we had a pair of 5s, and we had a 7 left over. So there you go. So again, if you're having to simplify these radicals without a calculator, get in the habit of doing your factor trees again. All right. That is multiplying. I could give you a FOIL problem and have like a binomial times a binomial. Then it's the same idea as with x's. Just everything in the first binomial times everything in the second binomial. You got to combine like terms, but before you combine terms, you're probably going to have to simplify to see if they are like terms. So if that was like if I gave you square root of 5 plus square root of 7 times square root of 35 minus 4 square root of 5, you're going to have 4 things to multiply. It's just a little messier version of what we're doing. I really wish I could, ask you other questions and you all have me, give me feedback on that. But there. So let me know, email me if go ahead and get in the homework, and then if you have more questions, got those examples, email me, and then we'll get you up to speed on that. But again, this is more of the pre-calculus sort of level. But the main thing, like with the quadratic formula, is what's outside the radical gets multiplied with outside the radical. It's inside the radical gets multiplied with what's the inside. That's the important part of it. All right. We're getting close to the end. All right. So for division of radicals, we're gonna, again, if this is a pure pre-calculus level course, we'd be doing a lot messier versions of this. We're just going to do sort of the basics on here. And so there's something called what we call rationalize the denominator. And what rationalize the denominator means is if you have a fraction that has radicals in it, we do not want radicals in the bottom. This would be considered an unfinished or incorrect form. If there's going to be radicals in a fraction, the radicals have to be in the top. All right, so how do we rationalize the denominator? How do we get that radical out of the bottom? Well, for these basic problems that we're doing, all you have to do is multiply top and bottom by the denominator. We're essentially multiplying this by 1. So this 6 over square root of 5, we're going to multiply top and bottom by square root of 5. Well, how does that help us? Well, on the top, how do you multiply 6 times square root of 5? Well, 6 is outside the radical, 5 is inside. So we don't multiply those at all. That's just 6 times square root of 5. And on the bottom, square root of 5 times square root of 5, well, that's square root of 25. Hopefully, as you get more comfortable with these, if you have a square root times itself, that just gives you the number on the inside because the square root of 25 is 5. So the final answer here would be 6 square root of 5 over 5. That's what we mean by rationalizing the denominator is we want to, if the radical's in the denominator, we have to basically move it to the top. And that's legally how we do it, multiply top and bottom by that denominator. If this was a binomial on the bottom, like like square root of 5 plus square root of 7, that's a much messier problem. We're not going to go there in this class. That is something like for trig that you'd probably need. All right, one more of these. All right, so again, I'm just kind of dipping our toe in the water for those that are moving on. So -9 over square root of 20. Now you might see examples that say, well, can that square root of 20 be simplified? Yes, but let's wait and do that at the end. I find that for most students, like simplifying the last step is a little bit more straightforward. So let's just multiply square root of 20 over square root of 20. Okay, so on the top, can't multiply that 9 times the 20 because one's inside, one's outside. On the bottom, we have square root of 20 times square root of 20, which is 400. And so now let's simplify. Well, if you need the calculator for the bottom, that's okay. But we're doing square root of 20 times square root of 20, so we're multiplying 20 times 20. So the square root of 400 is 20. You want to back that up in a calculator, then by all means do so. That top, does that simplify? Well, here's where let's just use the calculator. So -9 square root of 20 is -18 square root of 5. The where that's coming from is 20 is 4 times 5, and then the square root of 4 is 2. So 2 times 9, that's where we're getting the 18, and then that 5 is left over. Now, are we done? No, because we can still simplify. Here's where you have to be careful. And one of the reasons I'm still doing this, rationalize the denominator, even though we don't need it this class, we need to be able to simplify this. So here's a question. Do we simplify the 5 and the 20 or the 18 and the 20? Hopefully you're saying the 18 and the 20, because just like when you're multiplying, you can't multiply what's inside the radical with what's outside. Works the same way with division. So that square root of 5, there is no square root of 5 in the bottom. We cannot deal with that 5 anymore. So we can only simplify that 18 over 20, or the -18. Those are both even. See, the answer is negative, both even, so that would be 9 over 10, and then square root of 5 on top. So when we get to quadratic formula problems, we're going to have answers that may look like this. So you need to know that only simplify outside with outside. You cannot simplify something that's inside a radical, something that's outside. Okay. Let's go back to that idea of the rational exponents. This is definitely, again, this is something that we're going to see again when we get to logarithms. Okay, so let's play around with that a little bit more. So remember, if you have a fractional exponent, the numerator is the exponent on the inside, the denominator is the index of the root. Now, one thing about this, it actually doesn't matter like which one you do first. Notice that you could do the nth root of a to the m power, or you could do the a to the m power first and then do the radical. And it turns out, and the reason being is that a to the m over n, when you have a power raised to a power, you multiply them. And so you could do m times 1 over n to get m over n, or you could do 1 over n times n and still get m over n. So that's kind of what's going on there. Like mathematically, it doesn't matter if you do the exponent first or the radical first, just in general terms, but when we're simplifying numbers, it definitely makes a difference. So let's talk about that. So use the radical notation to write the expression, and here it is, simplify if possible. So when you have 8 to the 4/3 power, how would we write that with a radical? Eight's is the number on the inside. And so where does the 4 go? Where does the 3 go? Well, the 4, that is the inside exponent, and the denominator is the radical. So that's sort of what we're doing there. Or we could write this the other way around and do the cube root of 8 to the 4th power. So that either of those should be acceptable to MATLAB. And then again, they may want just the simplify part, but I'm going to, this is sort of intermediate step. We need this to be able to simplify. So let me ask you a question. Which one of these is going to be a more straightforward problem? Well, how big is 8 to the 4th going to get? If that's 8 times 8, which is 64 times 8, and then times 8 again, that's going to be a big number, right? And then you're going to get a really big number, and then you're going to have to try to figure out what times itself 3 times gives you that. I don't know about you, that sounds pretty complicated as a math problem, as an arithmetic problem. But what about this? So if you have the cube root of 8, what times itself 3 times gives you 8? That's just 2, and then 2 to the 4th, that's 16. So when you're dealing with simplifying numbers that have fractional exponents, actually doing the radical first is going to give you smaller numbers to deal with. I couldn't do this without a calculator. Well, I could do without a calculator, but it'd be some big factor trees because you got, so I don't even want to mess with basically doing factor trees with 8. And so you're going to get lots of 2's to deal with. So just if you're simplifying numbers with rational exponents, do the radical first. So let's try 30. We have negative 32 to the 1/5 power. So first of all, let's write this as a radical in radical form. But inside the radical is negative 32. All right, so where does the 1/5, how does that play in? Remember, the denominator is the index. So this is the 5th root of negative 32, basically to the 1st power. Well, can we have a negative inside that radical? Or is this not a real answer? Remember, it's the even radicals that we can't take odd negative numbers. But since we're going to have 5 of these, 5 negatives multiplied is going to give us a negative. Okay. So we know the answer is going to be negative. So now what number times itself 5 times gives you 32? No. 1 to the 5th is 1, 2 to the 5th. And so on these calculators, you have that's your exponent key. The 2 to the 5th is 32. That is -2. Okay. Now, one of the nice things is sometimes I see calculators that don't have this button. They're really basic scientific calculators. They don't have the X that, where you can do the 3rd root, 4th root, or whatever. But you could always do this in the calculator. One thing you do have to be careful of is there's is there parentheses there or not? Well, no, there's not. If there was parentheses around the whole thing, there would be parentheses. So that's basically negative 32 to the 1/5 power. Actually, now that I'm saying that, I realize that since there is no parentheses, I did that wrong. That negative should have been on the outside. The only reason that negative should have been on the inside is that there was parentheses around the negative. Can't believe I did that. But let's do this in the calculator. So negative 32 raised. Well, how do you do it to the 1/5 power? Do your parentheses. Now you could do 1 divided by 5, but there is that n over d button on these calculators. It's one reason I love them. So if you do n over d, it actually gives you the nice friendly fraction. And then arrow over, close out your parentheses. So negative 32 to the 1/5 power is -2. So again, ideally you can do this without a calculator, but practice your calculator. All right. So now let's do the next two. And explain to them why I was wrong by initially putting that negative inside the radical. Sometimes I even make mistakes especially when I get in a hurry. All right. So use radical notation to write the expression, simplify as possible. So how do we write 5x to the 2/3 in radical notation? Radical notation means I need some sort of square root cube root or so. So first of all, when we're dealing with a radical for this problem, what's the index on the radical? Square root, cube root, what? Well, the denominator is 3, so we're dealing with a cube root. Now the other question is, what goes inside the radical? So is it 5x, and since that 2 is on the top there, or is it 5 on the outside and a cube root of x squared? Which one of those do you think is correct? It's not the first one. It is definitely the second. And why is that? Well, it all comes down to parentheses and how we write our exponents. So if you have a term that has an exponent, if there is no parentheses, the only thing getting the exponent is what's immediately to the left. Okay, so since there is no parentheses here, only the x is to the 2/3 power. So only the x, or in this case, the x squared, should be on the inside. If you want that top one, that would be 5x in parentheses. Well, it's not even, well, that would have to do 5x squared, right? Because then the 5 and the x would have to be squared. So that top one wasn't right for anything. So be very careful about whether or not there are parentheses. So what would you do with 32? We have 3x parentheses to the 2/5 power. So we're going to have a radical. What's the index on it? Oh, it's a 5. So the denominator. This goes inside the radical. Parentheses is 3x. And it's squared, so we're going to square that parentheses. Now, I don't know if we get quite that messy in MATLAB, but if we do, one thing you have to be careful of is we can do 3x squared. That's 3x times 3x. And 3x times 3x would be 9 squared. This would be an equivalent answer. If this was a test, I may give you full credit for that. I may take off 1 point, but that would be the full answer because we need you to know that you're doing 3 times 3 because it is 3 squared. Does that make sense? Hopefully. Let's do a couple more, practice that. So on 33, write using rational exponents. So we're kind of going in opposite order because now we're starting with the radical and now we need to go the other way. We have the cube root of xy. All right, so first of all, do we need parentheses in or not? Well, yes, we definitely need parentheses because these are both inside the radical. So put parentheses around the xy. Now it says use rational exponents. That's giving you a hint that your exponent is going to be a fraction. So what's the numerator and what's the denominator? Well, the denominator is the index. That's going to be to the third. Now, what's the top? That's the exponent on the inside. Well, notice there was no, those were both to the first. So it would be xy to the 1/3 power. Or you get to x to the 1/3, y to the 1/3, because you could think of this as the cube root of x times the cube root of y. So I would accept both of those as fully equivalent answers. What you don't want is x to the y, xy to the 1/3. That would be bad. And why is that bad? Because there is no parentheses. So that's telling you that only y is getting the 1/3 power. But the x is inside the radical, that x also needs a 1/3 power, whether you do it separately or you do it in parentheses. Okay. One last example here. I will jump to MATLAB. So same idea. If you look at 34, we are writing in rational exponents, the square root of x to the 4th, y to the 5th. And just like when we were simplifying, I said like do x's with x's and y's with y's. So let's look at the square root of x to the 4th, the square root of y to the 5th. Now we're not simplifying. In this case, we are looking for rational exponents. So this is going to be x to some power and y to some power. And the powers are going to be fractions. So what is the denominator on both of these fractions? Well, they're both square roots, so they're both divided by 2. What is the numerator? Well, for x, it's going to be 4, y is going to be 5. Now, this we can simplify because 4 divided by 2 is 2. That's going to, that doesn't simplify to a whole number, so we're going to leave it like that. The final answer would be x squared, y to the 5/2 power. Okay, so you're starting to get a little overwhelmed at this point. I would say don't worry about it too much because one, you still get to do the homework and practice this, and two, this is even though this is still a little bit higher level algebra, I don't think it's like as heavy as the factoring part, and we don't use this much in this class. We're just kind of practicing this now. When we get into logarithms, we're going to use it a little bit here and there. And when we do the logarithms, it'll be more like writing, this in exponent form or this in exponent form, not together. So this sort of problem, just as long as you have a sort of a general feel for it, like for me, like a test question, I think something like this would be a better test question than a variable for this particular topic. Yeah, I don't know if that helps or not, but all right. That is the notes. Let's look at the homework right quick in MATLAB, see if there's anything I missed. So this homework is roots and radicals. Oh, I had my MATLAB turned off too long, or active. Here, let me get back in here. Get that shared like it was supposed to. All right, so when you open up the roots and radicals review, there are 26 questions, which is actually longer than some of our other assignments. But the reason this is a little bit longer because there's a lot of like small problems. This isn't like the factoring where like a lot of the factorings were long, kind of involved problems. So there wasn't as many of them. When there's larger numbers like this, they tend to be shorter problems. I'm aware of, like, I don't want to overload you with unnecessary homework. There's just a lot of little topics in here, so that's why there's more problems. Number one, this is a good little review. We just talked about this. And so this is a good place to start. So what's the difference between -8 squared with parentheses and without parentheses? Well, -8 squared means -8 times -8. So that's a positive 64. -8 squared without the parentheses means there is one negative. So that's the opposite of 8 squared. So that would be a -64. So again, anytime you're dealing with exponents, parentheses matter. The way I remember it is if you have parentheses, you have the same number of negatives as the exponent. So like if this was -8 in parentheses to the 5th power, you'd have 5 negatives. If you don't have parentheses, you only have one negative. This is all right. So then there's going through, you're going to have some square roots to simplify. You're going to have some cube roots to simplify. Again, they're going to give you that option of A or B. Is this an actual numerical answer or is it not a real number? Remember, we can take odd roots of negative numbers. We can't take even roots of negative numbers to get a real number. So if this was the square root of -1, then the answer would be not a real number. Since this is a cube root, well, -1 times -1 times -1 is -1. So we can get negative. We can have negatives inside the radicals for odd roots. All right. And again, a lot of these earlier problems, try to do it, especially with the square roots, try to do it without a calculator. Remember, you do have the calculator as a backup. Most of the problems we're going to deal with are either square roots or cube roots. Watch out for that. We've talked about this. Let's see, there's one thing. Like here, this is the 5th root of x to the 30th, y to the 20th. This is where I talked about you could do the grouping method, but you're going to have to write out 30x's and 20x's and then look for groups of 5. Or if you use the division method, 30 divided by 5 is 6 with no remainder. So you're going to have an x to the 6th on the outside. And then 20 divided by 5 is 4 with no remainder. So you're going to have x to the 6th, y to the 4th. This is where I want you to try that division method for problems specifically like that. Okay, and then we get into the adding subtracting. These are both square roots of 7, so that would just be 17 square root of 7. Except for the adding subtracting, I didn't really get too messy. Oh, by the way, I like throwing these definition style problems in there to just kind of help with the language. If you're ever not for sure on the definitions, that's where the textbook is a good place to go. All right. So if it's not in the notes, if you didn't watch the video, I guess you're not getting this hint. But the textbook, this is R8. So this is review chapter section 8, number 7 in the homework. So if you go to the textbook link, it's going to take you directly to the review 8 section. And the textbook is always a good place to find definitions. Right, there's a couple of rationalizing the denominator. Like on this one, you'd multiply top and bottom by square root of 14. One of those. And then there's some of these with the numbers. Let's see. So like all these that we did at the end are all just actual numbers, not with any of the variables in there. But I threw those variables in the examples to kind of give you, I really want to kind of emphasize the parentheses idea. And later when we get into logarithms, you may see a few of those. All right. So it looks like I didn't miss anything from the notes and the homework. So get in there, see where you have questions. As always, don't forget about that Ask My Instructor button in the homework under the Get More Help. Sometimes it just says Ask My Instructor. If you use that, it will send me a link to your problem with your numbers. And as always, it really helps me help you if you put in an answer or if you give me a specific question. So for that's it for this topic. Next video I'll be doing will be the 1.1 solving linear equations. We'll get into some more algebra, but now we'll be getting into solving. So we're kind of changing the theme of what we're doing with the algebra. Have a good day.